Hello, everyone. Okay. So we have some syllabus there. If you want the hard copy, you can grab one. Okay. Yeah. Just give me a second. Write a few things and then you're gonna officially start. Okay, hello everyone. Welcome to the second part of our course. It's good to see familiar faces and some new faces. One question. So people who are new I assume you have never taken any version of this course in previous years. Do you have any familiarity with online algorithms, online learning? Should I assume that you know the basics, or should I cover some of the basics as we go? Do you want actually let's do a round of introduction.
Hi, I'm Salino. I'm a PhD student in the computer science department, working with Lorenzo Recchia in convex optimization and spectrograph theory.
All right.
I'm auditing.
You're auditing. Perfect.
I'm Chen. I'm a postdoc at Chicago Booth. Nice to meet you.
My name is Percy, a first-year PhD student at Chicago Booth, majoring in econometrics and stats.
All right.
I'm me, also ENS first year student.
Okay.
I'm Alicia. I'm also ENS first year student.
All right.
I'm Pepe. I'm a second year in operations.
Babu, I'm first year in operations.
Mama Rizal, first year at operations.
So you will also first year in operations management.
Angelina, do you want to introduce yourself too?
Hi. Hello. Good afternoon. My name is Angelina. I'm a second year PhD student in operations.
Perfect. So I'm Rod, second year professor at Adwords. We have Varun. Varun, do you want to move?
I'm also NCO faculty.
Hello. We are doing a round of introduction. Do you want to introduce yourself?
I just sit here first.
Well, you can sit here if you want.
Okay, no problem.
Take your time. So in the meantime, let me do a little bit of logistics.
I'm sitting here.
Which department?
Just applied math.
Applied maths. Excellent. All right, so a little bit of logistics. So this is the first lecture. We are gonna have 9 weeks. The first 8 weeks, by default, I'm gonna teach and we're gonna cover several materials. So you have the syllabus, so you will have a sense of what topics we're gonna cover this week. Then there's week 9, in which the idea is you're gonna actually present a mini research project that you're gonna work on throughout the quarter. So there is no exam, there is no homework. There are 2 great components in this course, a mini project, and then the second one is ascribing the lectures. So we have, okay, so during week 9, you're going to present your work. We have one option, but we need your vote in order to go ahead with that. So I can also teach on week 9, and then we reserve another 3 hours for your presentation. If everyone agrees, we can probably do that. And the reason I'm saying, if you look at the syllabus, there are 8 topics and there are 2 tentative topics that I think they're important and interesting, but I need time to cover those. If everyone is willing to, we can have 9 weeks of teaching and then an extra 3 hours for your presentation, or we can have just 8 weeks, the default 8 lectures, and we are not going to cover any of those 2 tentative topics. You don't need to answer right now. Take your time, look at the topics, and let me know next time what's the plan. So the projects are going to be individual, so only people who take the course for credit should do the projects, and only people who take the course for credit should ascribe. Auditors definitely are welcome to ascribe if you want, but because it's part of the grade for the rest of the class, we're taking it for credit, we give priority to those. So if you go with 8 lectures, we are going to have 8 ascribes. So I need 2 eyes on each lecture. That means 16 ascribes. So if we do round robin, I guess each one of you in expectation is going to do 1.6 lectures. And we need 2 people to volunteer for the first week. So the idea is, you 2 are going to work on the first lecture together. Maybe one writes the half, the other one writes the second half. Then you sit together, edit everything, and send it to us. There is one thing about this quarter, because we have 8 lectures. I'm going to have actually a deadline for scribes. So the deadline is going to be the midnight of the next week's class. Okay? So we need 2 volunteers for today. All right, that's what I want. Yeah, the first thing is actually great how to scribe. I'm glad that we could find volunteers. Any questions about logistics? And we have 1 new person. So we did a round of introduction. Do you want to introduce yourself, Kshitij?
Yeah, hi, I'm Kshitij. I'm a 3rd-year PhD student at TTIC. I've been working with Rag, and I attended the first part, so love it. Yeah.
Any questions about, yes?
Would you please not write with red or green? It's hard.
Oh, okay.
Okay.
Red or green? There is no green, just one. Oh, okay.
Oh, I don't have green. I mean, I'm using.
Now
my
it's
own
okay.
markers.
It's
So only black and okay.
and not like Angelina says she can't read. So maybe you can write slightly better for her sake.
Even she can't read these.
That's what it seems like. But
I think if you go towards the light, it might be better.
that could be the reason. Yeah,
They're dimming the
on that side.
lights.
No, you should go towards the light because that is like in the dark.
I see. So starting from this one. Actually, I'm not gonna write anything here, so I'm gonna start from here. So this is just gonna get updated.
Yeah, I think that's fair because that's also furthest from the camera.
Alright, that sounds good.
Okay, next.
Okay, so we are gonna do a little bit of introduction about the course. Yes.
You want to change? I want to do his work.
Okay.
Actually.
Yes.
Okay, that's fine. Yeah, so a little bit of introduction about what we are going to cover. So the first 4 lectures are going to about some of the applications in market design and operations management, but more focused on online algorithms, online competitive algorithms. And then the second half is again on the applications, but we are focusing on online learning and search. So I need you to be familiar with the basics of competitive online algorithms for the first half. I try to have the lectures to be self-contained. So I'm trying to cover everything except probably like basic definitions. This is one difference between discourse and dialogue. So this is going to be a little bit less about like basics, or more on just like, learning the techniques and the results and the application. But if you have questions, interrupt me at any time and ask. That would be helping everyone. So we are going to cover two major topics today. The first one is basically how to design an online algorithm, optimal online competitive algorithm for a problem I'm calling search ads. I'm going to define it in a second. Then the second part of the course is a part of the lecture is going to be about an optimal online algorithm for display ads. When an ad exchange platform is trying to connect publishers to ad impression for opportunities. And then if time permits, I'm going to talk about a very general model that's actually covering or including all of those, called online whole page optimization. Probably we touch the surface a little bit. I tell you the model and the algorithm, and I leave the analysis for your exercise, own exercise. Okay. That's it. Any questions? If you don't have any questions, I'm gonna continue with the actual method. All right, cool. So, so the two topics I'm going to cover is about actually a multi-billion industry. So I was actually looking at numbers. The fourth quarter, Google made $75 billion in revenue. 62 billion was coming from ads. I think the distribution was kind of interesting, which is an indicator of where the interesting problems in OM are these days. So 25 billion was for display ads, 32 was for search ads, and then the remaining was for YouTube video advertising. Actually, the third problem is kind of like related to YouTube video advertising. I will be happy to talk about it offline more. But the search ad and display ads we are actually going to cover. And one of these algorithms, the Adwords algorithm that I'm going to show you in a second, is pretty much similar to one of the original algorithms that Google started with to match the search queries to advertisers and charge advertisers with appropriate money. Okay, so let's try to model this problem. So the search ad problem. What is the underlying problem? So we have a bunch of advertisers. Let me write down this like this. So they come to a search engine, like for example, Google, a platform like Google. They have a daily budget, which I'm denoting by B1, B2, all the way to, let's say, BM for the M advertiser. And then users go to the search engine, they start typing queries. So these advertisers are willing to show their ads, they're willing to pay so that their ads is shown when a query is searched by a user. So for example, you search for shoe, then there is Nike, then there is there is Puma. They are willing to show you different ads. So those are the advertisers that they are bidding for that search query. Then the task of the platform is actually picking a subset of these advertisers, or maybe one of them, as the winner, and then showing the ad of that advertiser to you. In fact, in practice, if you look at Google, there are 6 ad slots on top of the page. And when you search something, 6 advertisers are going to be the winners of an auction that is run in the underlying ad auction platform. And so Google is not only picking those 6, they're also charging them with money. So we are not thinking about the auction aspect of the problem, we're just thinking about the allocation aspect, which advertisers are going to pick. And especially we think about a special case when there is just one place to show an ad. So therefore, only one of the advertisers should be picked, and the ad of that advertiser is going to be shown to the user who has searched those search queries. But one important aspect of the problem is that these search queries are not known by the ad platform, in this case, Google upfront. So they're coming over time. And the way that we model that is basically we have an online allocation problem similar to the online matching problem that Varun covered in the last class. That's one side, the advertiser side is basically the offline side. And then queries arrive one by one. So this is kind of like the online side of the game. So once a query I arrives, all the advertisers who are interested in this query, they're going to bid for the query. So you get to see different bids. So if there's advertiser J, then advertiser J is going to bid Bij on the query I. And the goal of the platform is trying to match these queries to advertisers, respecting their daily budgets until the end of the day, so as to maximize the revenue they generate. Okay, so this is the budget on the money spent. This is the money that they pay. If you are familiar with auctions, basically you are thinking about running a first price auction, so advertiser bids something and pay his bid. And there is no incentive or game theoretic aspect. The problem is just the allocation problem. We match the arriving query to one of the advertisers. The advertiser is going to be charged with the bid, and game goes to the next time, which is the time that the next query arrives. Is the problem clear?
So this per day budget, the budget keeps decreasing every time they have been charged once.
Right. And the amount of decrease is equal to the bid that they. So, yes.
Can you say here the platform is kind of making decisions for leaders, and leaders now don't need to think too much to how they bid because the platform.
Right. So in modern platforms, there's this auto bidding in which the platform is actually making these bidding decisions on behalf of the advertisers. But in this problem, we are not considering that. Just bids are exogenously given to you every time that the query arrives. But there are two ways to think about that. So one is the bids are actually selected by the advertisers because the advertiser is running an ANSI machine learning algorithm to decide how much to bid based on the previous data. Or maybe the platform is giving them access to an auto bidding software and they're using the Google's auto bidding software in order to attend the auction. In this model, we are ignoring all of those aspects. We just imagine that the bids are given to you every time that the query arrives.
Yeah, and
But you don't know the future bids.
yeah, and my point is that even in all these scenarios, the result of matching would be somehow same, because in the end, the decision maker to match one bidder to one, and is gonna make a decision for the whole future of that bidder, considering those budget and everything else. So I guess somehow it wouldn't change a lot if we.
It depends on whether the matching decision between the queries and the advertisers and those bidding decisions for the auto bidder software are happening jointly or just like two separate entities. So here we are assuming the two separate entities. So bids are coming from an outside source. I don't care how are they generated. I'm in charge of matching the query stuff. Okay. So similar to last quarter's class, we are thinking about competitive online algorithms for this problem. So what does that mean? So our goal is to design an online algorithm and such that we basically maximize the worst case competitive ratio that this online algorithm gets in this problem in terms of generated revenue. Let me write it down. I'm going to explain. So we're looking at the minimum over all instances of the problem, expectation. You can have randomized algorithm expectation of alg I, and think of this alg I as the revenue that your randomized online algorithm generates as it sees the instance I, divided by the optimum offline solution, which is for the decision maker that makes a decision optimal in hindsight, knows the entire instance and picks an optimum allocation between the queries and advertisers. Okay. So this is what we call competitive ratio of this algorithm, and our goal is maximizing. So our goal is maximizing component image.
Expectation is over the randomness.
What is our expectation over the internal randomness? Yeah.
What does the optimal algorithm know?
What does the optimal algorithm know? The instance, basically the bits, the budget. The budgets are also the offline side. Both the in hindsight optimal and online algorithm, they know the budgets.
Right.
The optimal algorithm knows the bits. The optimal offline knows the bits. But the online algorithm only gets to see the bits as the queries are.
That's sorry.
Okay, is the in hindsight optimal? So it knows the bits they made in the past, and it has to make the allocation now.
Yeah, so imagine the time is fixed. So even the number of queries is what I call time. And is some number of queries. So this entire structure is known by the offline algorithm and picks an allocation between the queries and advertisers that respect the budget and maximizes the total collected leads. So that's the optimal offline. Online algorithm only gets to see these queries one by one. So once you see a query, you get to see all the bits from different advertisers, but not the future bits.
But the online algorithm also has access to the remaining budgets at each time step.
Of course, yes. So can keep track of these remaining. Yes.
Like, does the online algorithm know, like, for a given query that hasn't yet happened, what people would bid or no?
No, definitely you don't know. If you knew that for a query in future, what would be the bid? Then
I mean, you don't know that the query would come, but like, say, a query of type K, I know this would be the bid.
so there are other models for this problem, in which, for example, you have distribution knowledge about query types. Right? For example, that covers the type of thing that you have in mind. That I have query types, a type will give me a bunch of bids on the advertiser size. I don't know which type is gonna appear. If I don't know which type is gonna appear, I have no information about that. I just know the mapping between types and bids. Then this is really no information. But if you, for example, know that maybe the type distribution is IID or coming from this known distribution, then you probably can do something. Actually, in the next lecture, you're going to see something similar to that in the context of alphabetical optimization. But here, it's the adversarial arrival in the technical language. Yes.
If the queries are coming from non-IID distribution, then we can just say that I expect to have this many in the future and just solve the offline, right?
If you know the distribution, yes. If you don't know the distribution, then
You learn distribution again.
Actually, in the idea version of this problem, when budgets are larger than this, which is an assumption I'm going to make in a second for this problem, when you have IID arrival, you can actually get very, very good solutions, almost near optimal. But under the adversarial arrival, which is this setting, you are going to lose a constant. And let's actually discuss that. Yeah. So a bunch of natural algorithms for this problem. I'm gonna talk about those first, and then we are going to go to an algorithm that more or less you saw in the previous class, but I'm gonna dig very deep into it. So what are some natural algorithms? Actually, let me ask you guys. What's the first thing you want to try here?
Greedily, like just giving it to the highest bidder and like not thinking about how they might bid in the future or remaining bids.
Perfect. So greedy. What does that do? So once query I arrive, match the query to J star, such that J star is equal to the argmax of literally Bij over all J's that can accept the query. How about that? All J's such that Yj plus Bij is smaller than Bj. And I'm defining this Yj variable as, let me add it here. So blue is fine, right?
Yeah, blue. Thank you.
So I'm gonna have y1, y2, yn. These are called spent variables, or maybe the current level of consumption. It's like how much money at this stage of this online process each advertiser has spent. So at the beginning, it's 0, it goes up, it can never go above the budget. So this is basically literally means that, if there's an advertiser that can accept this bid because it has enough remaining budget, among those, I'm going to pick the one that is the highest.
It doesn't matter how we break ties, or would it not matter?
Let's say there is no tie. So it's like, if we are in general form, so there is really no tie. But it doesn't matter. So how bad this algorithm can be? Any guess?
1/2.
So it seems it might be half. Do you know an example that makes use of a half approximation? Yes.
You have, it's the first bidder exhausts all of their budget in the first, let's say the first query. And then no one bids on the second query, but someone would bid the same, the first. So in this case, you pay B1J as your profit, and in the other one you would get twice that, because in the first query you give to someone else.
So it's kind of like in the first round, there are two options. The advertiser can basically all the arriving queries can go to one advertiser or the other one. So one is the right one because the other one is going to be used in the second round, but you don't know which one, so you go with the one. So this is roughly the intuition. So let me actually try to formalize it. So imagine I have two advertisers on the right side. Okay, so I have two advertisers. Each one has a budget of $100. Okay. Here's what I do. So imagine 100 number of queries arrive at the beginning. So this advertiser is, if you look at each of these queries, this advertiser is bidding one, let's say plus epsilon, this advertiser is bidding one. So the greedy algorithm is really just like matching all these queries to the first advertiser. But then I'm going to make this advertiser the wrong one. So in the second stage of this game, 100 queries arrive. And you want this to be the wrong one. So so this guy is bidding one on each of these queries, and this guy doesn't have any bid on these queries. So what is optimal offline? So optimal offline is basically, I'm going to give all these queries to this advertiser and all these queries to this advertiser. I'm going to make a revenue of 200. So opt is 200. But greedy, where it gets to see these queries, let's say one by one, during the first half of the game, doesn't really know that these guys are coming. So it's going to always assign all the queries to this advertiser. Then these queries come. This guy has ran out of budget. And therefore, you can't match any of these queries. So greedy gets something like 100. Almost 100.
N is 200 in this example? Small n?
N is 200, for example.
So, okay, but so something less than 100 is what you're saying the first one bits.
The bits are they're one process. So it's just like a number of these guys. So it's like 100 queries. I could make an example in which the budget is 1, the bits are 1, and there are only 2 queries out.
Yeah.
But I wanted to make the bits to be smaller than budget because it's an assumption we're going to work with, and even under that assumption, still you cannot do better than 2 by just going with the greedy algorithm. Yes,
We don't have buyback.
No, you haven't. I wish you had. No, actually, bipartite doesn't help here. So the gain that you get is exactly equal to the bit that you have on each edge. Because and the same amount is going to bring down your budget. Therefore, there is really no. So it doesn't matter who is using my budgets. Query in the past or query in the future. The same amount of budget has the same value.
The problem is I have an example in my mind, which is infinity, not half. I mean,
No, so again, so the problem is, so this is not a budget on the number of queries you can assign. It's a budget on how much money you can assign. And the bid is the money that you pay. So the total bid that you pay cannot exceed the budget, not the total number of.
can I give an example? So if there are two online nodes
Mhm.
and one bidder, the first one is connected with epsilon,
Yeah. this
yes,
one. Mhm.
and the other one is the capacity B, capital B.
Okay, so this bid is B,
Yes.
But you can't bid more than your budget.
So that's what I'm saying. So this online,
I think for both ones be on the capacity. So once you spend epsilon, you can't match B because
yeah,
Okay, well,
so it's violating the small bid model, I think.
right, so in fact, there are two versions of this problem. So the first version is you can do bid capping. What does that mean? So that means that if the advertiser has some remaining budget, like bid maybe a high amount, the advertiser can still get this query, but it's only gonna pay for how much budget he has. In that case, this algorithm is gonna be a half approximation studied period. I'm gonna show that. Without bid capping, only if you have an assumption, it should be a very small amount budget, then this algorithm, as I'm writing it down here, is gonna be a half approximation. But so there's a bid capping version. I was trying to actually cover that too. Let me do it right now. So in this version of the algorithm, if there is no room for the extra bit, then you just don't assign the bit to the advertiser. You can think of a version in which let me write it down here, the bid cap version. It's just it's not a different algorithm, it's actually a slightly different model. So in which I'm replacing BIJs with basically the minimum of BIJ and BJ minus YJ. So what does that mean? That means if I assign I to J, if J can get the bid, it's gonna enjoy revenue of BIJ. If cannot receive the entire bid, the revenue is gonna be this term, which is BIJ hat. Okay. So you can still assign the bid to an advertiser that doesn't have budget for that bid, but then all the money that you make is only the remaining budget of the advertiser.
This is essentially relaxing the integer constraint.
For just the one last bit. I'm not assigning bits fractionally all the time. Just like one last bit can be assigned fraction.
That you have to do in this example also, because after the 99th bit, the first on the first 100 items, the first one can only.
This is almost 100. So.
Yeah, so like it's like 99 plus 99 epsilon.
Okay, so this is the bit capping version, it's just a slightly different model. Let's actually first analyze this version under. So we are going to do two things. The theorem one. If the max of bid over budgets, where all ij's is smaller than epsilon, then greedy is half minus order epsilon conflict.
so that's why my example was.
Right, but with bid capping, your example also does.
These are non-segment price options, right? These are not second price.
They're not second price. So you could define a second price version that, hey, the first point when I define the second price version, you need to be more careful. So you need to assign a subset of advertisers to each search query. There's a version of this problem that each time you assign a subset. Actually, I'm going to talk about assortment optimization in the next lecture, which is more or less of that nature. And then you could define the revenue would be the second highest bid in that set. Here, because it's first price action, I'm just picking a winner and force the winner to pay. Yes.
What do you mean you only pick up the last bid?
Right, so by last I really meant like the one bit that you need to break in order to fit it into your budget. So imagine I'm an advertiser, my budget is 100, I'm receiving like different bids of size 1.5, right? Until my spend is like, I don't know, 99.5, I don't need to do bid capping. But then when I receive the last bid,
What's the difference between doing it or not doing it? Because
Farmer's example. So in
the previous one, not
previous one, you mean?
up until that you arrived to 99.5.
Oh, so there is a fractional version of the problem in which, even if I'm a bidder, I have like BIJ, so not a bidder, a query arrives. Different advertisers are bidding on this query. So you can't even break this query and give like half BIJ to this guy, half BIJ. And you're actually going to do that a lot of times this lecture. But I just wanted, because Chen mentioned that I'm.
But for the greedy algorithm, you will never break them.
Sure. For the greedy doesn't need to break, but I just want to say that it's not like fractional problem. I will still take out the integral problem, but it is cabinet. Okay. In the interest of time, let me actually do a quick answer. So theorem 2, in the bit cap version, greedy is half complex. So before proving these two theorems, let me start with something simpler. Can you think of like an algorithm that breaks this example and does the right thing? Just a simple algorithm. Right. So I'm saying like, so the queries arrive, there are two advertisers, they are more or less the same. What should I do? What's another natural thing to do?
Randomly giving just to whoever has bidded something non-zero.
Right, so basically they're giving like 50 of these queries to this guy, 50 to this guy, right? So there is a version of this thing which is called balance. That means that I'm ignoring the bids. It's very stupid algorithm, but works actually very well on this example. So I'm ignoring the bids. I'm always allocating to the advertiser with the least money spent so far. So the guy that has the maximum remaining budget, I'm going to go with that. So if you think about that algorithm here, so 100 queries arrive. So you basically give like the first query to this guy, then the second one to this guy, then the first one to this. So 50 queries go to this guy, 50 goes to this guy. And actually here, this is the right thing to do because, well, the right in some sense, so you're going to beat half. So then when these guys arrive, only 50 queries or the $50 of the budget of this advertiser has been mistakenly used in the first round. Therefore, you can allocate 50 queries here. So then the algorithm gets 150, up gets 20, which is a competitive ratio of 3/4. Way better than half, and this is fantastic. This is actually the optimal algorithm for this problem, for this instance. The optimal online algorithm for this problem. If you don't know what's happening in the second stage, the best thing to do is dividing 50-50. So
I'm slightly confused.
Yes.
Sorry. So why did we introduce the bid cap version? Since the algorithm as well as the optimal, everyone gets to know the budgets. No one would ever give the item to a bidder who has like overshot their budget because they know they can't fulfill the payment.
Yeah, you could get around this by saying that, oh, well, so
I mean, the definition of the problem already implies in my head that the version should be the bid cap version. Like, why would I even entertain a bid which is higher than the budget?
no, but here it's not about the budget, it's about the remaining budget.
Yes, the remaining budget. why would I entertain
Okay, so if you, yeah, so then you could just define the problem. I think you're saying the same thing.
Yeah, we are saying.
So you could either embed this in the definition of the problem, or just like calculate the revenues in this way.
Yeah.
It's the same. All right, so let's actually write down the balance before we get to the proof of this thing. This is gonna be our first Primal-dual analysis when we prove theorem 1 and 2. So balance. So once I arrive, allocate I to J star with the smallest right. I'm just writing it in volts. Can you think of a very simple example that kills balance? Like claim that balance can be unbounded with that. Why always going with the advertiser that has a smaller spend? It's not the right thing to do.
Because one of the edges can be infinity, and the yj is slightly positive.
And the Voyager, I see. So yeah, I think you're saying more or less the same thing I had in mind. So
It's something epsilon to epsilon 3 epsilon 4.
okay, so basically imagine I have just 2 advertisers and 1 online. So there are 2 advertisers. Oh, I'm gonna have more than 1 online.
You don't need more.
Let's actually have 100 online.
You can do it with one, and you just need a lot of queries, I guess.
Right. So let me do it in the file. So something fundamental goes wrong when you do it. So when, let's say a bid arrives, imagine that both of them, again, they have capacity 100. It really doesn't matter. So the first bid arrives, this guy is bidding, let's say 1. And then this guy is bidding 0.01. Okay. Let's say I assign the first bid to just like this guy. I mean, it's a tie, so I just go with this one. So now the yj, so you assign this. So now yj, y1 of this guy becomes 1. Very important. Now the second bit comes, again, the same situation, 1 and 0.01. So even if you assign 100 of these bits to this guy,
Sorry, why not 100? The second edge. If it's 100, it's enough.
if I make it 100, but yeah, I get even with bit capping, this algorithm is going to be very bad. So you're right. I mean, I can make it large and then you're right. But with bit capping, even this can be done. Because so when this query arrives, you really need to match 100 of these queries so that this advertiser become more attractive than this one. Because these guys, money spent goes up step by cent by cent. So it takes 100 steps until it gets to y1 equal to 1. So you always go with this guy. And now I'm going to literally give you 100 of these things, 100 queries, exactly the same. So the balance algorithm is going to match everyone to this advertiser. So balance, how much money does it make?
101.
No, it doesn't even get to 100. So 1 in the first round, and then only $1, almost $1.
Oh, sorry.
So balance is almost like 2 ones. But then, what is the optimum? 100, right? So you could just
100 plus 0.
allocate everyone to the top guy. So up should be 100. And this 100, you can just escape it. So this essentially shows that balance is unbounded. Okay. So greedy, Seems to be half aperture bias is unboundedly bad. Keep those in mind. Let's actually try to prove this theorem. I'm just gonna, in the interest of, I'm just gonna prove maybe this version, and I'm leaving this version as an exercise. It's actually a cute exercise. Okay. So let me. Okay. So proof of theorem 1. We are going to use the theorem of linear programming and the Primal-dual proof to show this theorem. Basically, we are going to use the allocation created by the greedy algorithm as our primal solution. We are then looking at the dual of a linear program for optimal offline. Then we show a very simple dual assignment that is certifying the approximate optimality of try. If you haven't seen Primal-dual proofs, don't worry, I'm going to explain them. Brief. So the first step is actually writing a linear program for optimal offline of the problem that I just erased. So let's write it down. So we are trying to maximize summation over all queries, all advertisers, Bij, Xij. These are my decision variables. So think of them as fraction of query I assigned to advertiser J. So we're trying to maximize this subject to 2 simple knapsack constraints for any query I. You just want to give it to one advertiser, so the summation over all J's from 1 to m, Xij is at most 1. And then for every advertiser J, you don't want to exhaust her budget. So the summation of Xij, Bij over all the queries should be no more than advertiser costs. And of course, Xij should be relevant. Yes.
May I ask a question about that?
Yes.
What if, for example, the first person bids 100 there,
Okay.
and the second person, yeah, and the same situation.
I just want to show you that it's going to be unbounded, even these are smaller than budgets. So that example quantitatively is the same. That was your point. That also. Right. So going back to this, so I'm going to call this guy the primal program. So we're going to use duality. For each constraint, we're going to have a primal, we're going to have a dual variable. I assume that everyone is familiar with LP. People who taken the previous version of the course, the part 1 or Varun's previous course last year, they definitely know, but I assume everyone else also knows. If you don't know, we can chat about it after the class. So the dual variable corresponding to this constraint is called that alpha I. And the dual variable corresponding to this constraint, I know beta is bad, but I'm going to use it again because we have P and beta, so this is just beta J. So that means that I'm trying to minimize summation alpha I over all queries plus summation over all advertisers, Bj times beta J. This is the objective of the dual. And then you have to cover basically every edge that connects a query to another edge. So that means for every I and j, you want to have alpha I plus Bij times beta j to cover the money on that edge Bij. And alpha and beta should be not. So this is the dual problem.
Could you repeat the reasoning for the dual constraints?
Where is this coming from?
Could you just repeat what you said
Yeah.
about
Yeah, so basically, the idea is, there is a transfer on each edge, which is equal to Bij. And then the two sides of the transfer, the adds and queries, they should actually cover that. So the query is pushing alpha I amount, and the advertiser is pushing Bij times beta j. This is one way of thinking about duality in general for packing problems. But if you don't like that, just think of it as I'm multiplying this constraint by beta j, multiplying this by alpha I, and beta j times Bij plus alpha I times 1 should be covering the value, the coefficient of the primal variable Bij, and that gives me this constraint. Okay. All right, so we have the algorithm written here. I'm going to show you how you can construct a simple dual assignment that shows that this guy is half minus epsilon. This is pretty similar to things that we saw last quarter again. I try to so just to make it clear, so every time that you match I to J star, you set Xij star to 1, and all other Xij's are 0 in this primal assignment. So as for the dual, so here's going to be my suggested dual. Every time that you do this, every time an allocation happens, that means I has been assigned to J star, set alpha I to be Bij J star divided by 2, increase beta J star by something like Bij star divided by 2 times Bj. Okay. So 2 claims. Claim number 1. Every time you match, every time you allocate, every time I gets matched to J star, the change in the primal objective, when I write down delta primal, I mean the change in the primal objective. Change in the primal objective is exactly equal to the change in the dual objective. Proof. So when the match happens, how much primal objective changes? Delta primal? Bij star. Bij star. And how much dual changes?
Bij star over 2 plus.
So it's going to be the delta alpha I plus Bj star times delta beta J star, which is equal to Bij star divided by 2 plus Bj times beta Bj star times Bij star divided by 2 Bj star. And then there's a star here. Sorry for the typo. So this cancels this, and this is going to be equal to Bij star, which is equal to delta prime. So claim number 2. Dual is half feasible. So what does that mean? That means that so if the dual was feasible, then this would have been the optimal solution. Because you have a feasible dual, you have a feasible primal, the objective is equal to each other, and this is the optimal solution. But this is actually going to be half feasible, meaning that for every Ij, we are gonna have alpha I plus Bij beta j to be greater or equal than Bij. And one important point, this is not only for edges that you use in your allocation. This should be true for any pair of impression and advertiser noise.
What's B over two? Bij over two?
Yes, thank you. This is why it is half. This is the proof. It's quite easy. In fact, it's gonna be half minus epsilon visible, and we will see the second y. And just as a reminder, what is epsilon? So epsilon is the maximum or the upper bound on the maximum bid over budget. So the ratio of bid over budget in this problem is small, and it's capped by some epsilon. This epsilon shows it itself. Let's try to show that. So there are two cases. Case one is that suppose, let me write it down, case one. Suppose Bij could fit into J's remaining budget. At the time that I arrive. Basically, I'm looking at the time that I arrive. Scenario number one, J has enough remaining budget that will be one of the contenders in this maximization program. It is like one of those advertisers that potentially can get the bid, but probably doesn't get the bid because it's not the highest bid. So if that is the case, then I can say, well, alpha I plus Bij times beta j is equal to, so, right, so what is alpha I? So it is equal to Bij star divided by 2. And then we have Bij times beta j. But then the thing is, this is greater or equal than Bij divided by 2, right? Why is that? Because, well, we are assigning to J star. J star is definitely an advertiser that could fit the bid. J could also fit the bid, had enough budget to accept the bid. So therefore, Bij star should be greater than Bij. And therefore, this is just greater or equal than Bij divided by 2. As simple as that. I'm just ignoring any impact that the offline door can. The case one is the easy case. Case two is basically if, suppose, essentially Yj plus Bij is greater than Bj when IRS. So this is the case that the advertiser cannot actually access the budget. Then we can say, let me continue here. Then we can say alpha I plus Bij times beta j. This is greater or equal than so think about this beta j. So every time that someone is actually using your budget, is assigning a Bij divided by 2 Bj. So basically, every time that someone is using your budget, so your dual variable is going to go up by Bij divided by 2 Bj, right? So that means basically the dual variable of a vertex is always equal to Yj, the spend, divided by 2 times Bj, right? So from the assignment, I can always say that beta j is always equal to yj divided by 2 times bj. That's the nature of this dual assignment. Is it clear? So every time that, so imagine I'm some advertiser j, there are different queries that can be assigned to me. Every time that something is assigned to me, my dual variable is going to go up by the bit, and this is how much money I spent in that round, divided by 2 times my budget. So the 2 times budget is fixed across different queries. And then the summation of everything that is assigned to me in the past is going to be how much money I have spent so far, which is budget. So at any time in this process, budget is equal, bj, the beta j is equal to yj divided by 2 bj. And therefore I can say, so alpha is greater or equal than 0. And then this is greater or equal than yj divided by 2 bj. Then I know that yj is greater or equal than bj minus bij. But this is greater or equal than 0 plus bij times bj minus bij divided by 2 bj. So that gives me bij times half minus bij divided by 2 divided by bj itself. And this is greater or equal than bij times half minus epsilon because the ratio of bid over budget is at 1/6. All right.
I think you missed one divided by
Did I?
Bij divided by 2 bj.
2 bj. Excellent. So this is half, okay, I see. So this is half times 1 minus epsilon. Sorry. I'm using all sorts of context. Thank you. Bij times 1 minus epsilon. All right. So this is great. Why is it great? Because then I can say, for people that haven't seen this trick before, if you multiply your dual by 2 divided by 1 minus epsilon, this dual assignment by 2 divided by 1 minus epsilon, then it becomes feasible. But then how much the dual objective in total changes is going to be multiplied by 2 divided by 1 minus epsilon. So now I have a dual solution that is feasible. And I know that the objective of the feasible dual is now equal to what? So the previous dual's objective was equal to primal. Then you multiply by 2 divided by 1 minus epsilon. So it's going to be equal to the objective of the primal. Let's call it actually primal itself. Times 2 divided by 1 minus epsilon. Right? At the same time, we know that from the strong duality is a feasible dual. And dual is a minimization problem. So therefore, this is greater or equal than optimum dual. I mean, this part is just like because it's feasible. And then because of a strong duality, we know this is equal to the optimum primal, which is what we know as optimum of line. And now you see that I have established an approximation factor. The primal now is going to be greater or equal than 1 minus epsilon divided by 2 times dual, which is half minus some order epsilon. Exactly. Just to clarify the last step, so feasible dual is dual, the previous dual. Or we had a term for this, right? So for the dual that was non-feasible. Yeah, so that thing multiplied by 2 divided by pre-dual. So previous dual, right? So pre-dual multiplied by 2 divided by 1 minus epsilon. Okay, so grid is half approximation is tight. Basically, yes.
I'm confused by the terminology, I guess, but 1/2 minus epsilon feasible is like 1/2 minus epsilon optimal, or what is that term?
So dual is half times 1 minus epsilon physical. This is the meaning.
So what does this mean?
Dual is half times 1. So this is the meaning. So this is what it means. So it means that for every edge, so if you have alpha I plus bij times beta j was greater equal than
I see.
bij.
We have proven the second part, so we have also proven the first part in that case, right?
But this is just this was just like fancy terminology for this statement. This is the mathematical statement we proved. I'm going to use this C feasible in the remaining of the lectures, just want to define it. Okay. So, it's so slow. So let's try to prove. Or maybe we can have 5 minutes break. Do you guys want me to continue, or do you want to have like a short break? Maybe we can continue for another 15 minutes, and I'm going to show you the Adwords algorithm, and then we can have break. So we saw that grid doesn't work. I mean, you cannot do it on half approximation. Balance in the instance for which greedy was half competitive could do a good job. And in fact, I erased the example for which balance was bad. So in that example, greedy is optimal, right? Because greedy is really like going to go with the highest bidder. So greedy is really good. So the main question is, how would you actually kind of like mix balance and greedy in order to do that? So there are many ways of thinking about this problem. There is one way that I in particular like, and let me actually do that. I cannot erase it because I got erase it. Can I erase this part of the book? So suppose magically I give you access to optimal dual variables of the problem. So still it's an online problem, but then the magician gives you optimal dual of this LP. So you know the beta J stuff. How would you design an online algorithm that uses this information? I claim that using this information, you can actually design an online algorithm that is as good as the optimal offline. How would you do that? It has something to do with complementary slackness. The linear program.
Oh, you use those to get the. No.
Please repeat your question. So suppose a magician, for the actual instance of the problem, gives you access to the optimal dual variable beta J star. So you know these numbers. Beta 1 star all the way to beta n star. Can you design an online algorithm for this problem that is optimal? With this side information.
So this is information from the future itself.
Yeah, but not the instant, just like the dual variable.
So you look at the bits at each point of time and then see if the dual constraint is tight, given the dual parameter. If it is tight, then the primal variable is allowed to be loose, and we are also assuming xij is integral, so then we can clearly obtain from there whether it's one or not.
I like that. So let's think about this dual constraint. Alpha I plus bij beta j is greater equal than pij. So what does complementary slackness of the LP tells us? Complementary slackness. It basically says that, hey, if I look at each ij, either xij star is 0 or I know xij star is greater or equal than 0, and then the corresponding dual constraint is going to be tight, meaning that alpha I is actually exactly equal to Bij times 1 minus beta j star. This is the optimal dual vector. Right? This is just complementary status. And in fact, it tells you something more because the dual should be feasible. So for every ij, you know that alpha I plus Bij times beta j is greater or equal than Bij. So that means that alpha I is always greater or equal than Bij times 1 minus beta j for every I and j. So what does that mean? That means that xij star is only greater than 0 if j is basically the Rmax of Bi, let's say j prime, 1 minus beta j prime over all j primes. Right? Because alpha is always greater or equal than this for this particular choice, it is actually equal. Therefore, this is going to be the maximum. Right? So now you see where is this going. So I should like max, right? So think of it this way. So this guy is greater or equal than all of this. So this is going to be the max. But if you want to set alpha I should be the minimum over all these Bij. You're right. But basically, for the one particular j that this is tight, this is always greater or equal than all other j's. That means that if xij is right? Yes.
And what if there is no xij star greater than 0?
But if there is no xij star, then we're in this form. That's the complementary status, right? So either this is 0.
No, I mean in your statement.
So if for example, if all the beta j stars are greater than 1, then I'm gonna go with xij star 0. So here you actually need to look at all the j primes where essentially beta star. I mean, it is implicit, but let me write it down anyways. If something is small, greater than 1, then that is not going to be.
How do you break the ties?
It doesn't matter. It doesn't matter. So you can just go with one of them.
Anyone?
Any one of them. And the duals are picked in a way that no matter how you do the tie breaking, you're going to have a feasible solution.
I didn't get it. And for example, j is argmax.
J is Rmax.
Why xij star is greater than 0?
No. So what I'm saying is, complementary status is telling me that if in the optimal solution you assign query I to advertiser j, if you do that, I'm not looking at the case that xij star is 0 for all the
But
j's.
your arrow is two-sided.
That was the issue. Okay, that's all I need. That's all I need. But actually, you can say something a little bit more than that. I'm not gonna prove it because it's actually pretty easy. So in fact, if I give you the optimal ones, so the optimal solution is just assigning to the j that maximizes Bij times 1 minus dual. To just see that, think of Lagrangifying these constraints, multiplying this by beta j, bringing to the objective. And then you merge that with the primal. So now you don't need to be worried about the feasibility. So if I give you the optimal duals of the LP and I tell you, hey, maximize the Lagrangian given this optimal dual, then you are looking at Bij times 1 minus beta j star as the coefficient of each xij. Then the optimal solution is just like going with the one that maximizes quantity and pushing it all the way to 1. Okay. So basically, in order to be as good as optimum offline, you don't need the entire instance. This is all the information that you need. So an online algorithm that does the following, the online bit magician. So once I arrive, I'm kind of like running greedy, match I to J star, such that J star is the one of the argmaxes of Bij times 1 minus beta J star. So if you do that, then you're going to have the optimal offline. So this is a practice that is called kind of like bit shading, meaning that I have a bunch of advertisers. I want to hedge against uncertainty in the future or the adversarial input in the future. So all I need to do is shading or breaking down the bid of each advertiser by a factor, which is 1 minus the optimal dual of the advertiser. And then I'm good to go. So then I can just like run greedy and match to the advertiser who is the highest virtual bidder or highest bidder after you shade them. Yes.
And we're going to replace beta with the second line.
I'm going to do even smarter than that. So, so let's think about beta. So beta is also connected to complementary slackness in the way that if beta j is greater than 0, what does that imply? Beta j star.
Oh, that your constraint is tight?
That my constraint is tight. So I've used the entire advertiser's budget, right? And somehow, when you think about this, so you want this beta to be connected to the consumption level of the advertiser. So if the consumption level of the advertiser goes up, you want the beta to go up. And somehow in this way, you get somewhere between balance and greed. Because if I imagine that beta j is not given to you by a magician, but you're actually constructed as the online algorithm as you go through different queries. As the queries arrive, you try to construct this somehow. And the construction you have is monotone with respect to the consumption level. Basically, you always keep this invariant that beta j is monotone increasing as a function of budget. Then if I just ignore this term and I give the query to the one that maximizes 1 minus beta j star, this is balance because you give it to the advertiser with the smallest spend. If I don't shade, it's going to be greedy. But then when you do the multiplication, it's finding a trade-off between greedy and balance and tries to be better than both of them in some sense. And this is exactly what the Adwords algorithm is. So Adwords, Mehta Saberi, Vazirani, Box 2005. So this algorithm is basically the following. Once I arrive, match j to, so at the beginning you set all the duals to be 0. So once I arrive, you match I to j star such that j star is the argmax over all j's Bij 1 minus beta j. And then you update the dual beta j such that beta j is equal to some function g of the normalized budget of the advertiser. So here, after you match this thing, don't forget to update Yj. So Yj star is going to be the Yj star plus Bij star. Then only update beta j. You don't need to touch all the beta j's, only the one that you are assigned to. You change is money spent. So update beta j star such that beta j star is equal to g by j star divided pj star. But this is an invariant that you are gonna keep throughout the array. And what is this g function? So we expect g to be kind of a mapping from 0, 1 to 0, 1. We're gonna come up with this mapping. Just give us a second, let me finish this and then. So we need g of 0 to be 0. And for now, these are the only restrictions I have on g, but we are gonna have more in the future. Yes.
Do you have intuition on like how, because here we're trying to balance two objectives. I feel like the way we decided to balance them is just like multiply the two, sort of. So what is like is multiplication generally just the best way to do it, or is there?
No, we already saw that, right? Why the multiplication is the right way to do it. I didn't do the multiplication automatically. It came from complementary slacks. You see? I mean, if I give you the optimal betas, this is what you need to do, and multiplication actually comes from this metric.
I see.
Right? So I'm just trying to mimic the online algorithm with the magician information, but rather than having a magician, I'm trying to actually find an approximately optimal dual throughout the process. Yes.
Is that argmax over all j in the feeders, or?
Here, when you have the optimal, yes, you don't need to be worried about feasibility. Duals are set in a way that if you go with argmax, feasibility constraint is going to be automatically set. The econ term, the market clears. So there are market clearing prices. But here you need to be worried about that. So here, if your question is what I'm doing here, then this is a relevant question. So here I'm actually matching to all the advertisers that can fit my and this bigger question. Here I'm doing that. But here when you have the optimal dual variant, only the optimal dual variant, you don't need to be worried about it.
You mean always the argmax respect the capacity?
Yeah.
Is it obvious, or?
It depends on how good you know linear programming. So think of it this way. So like there are items, there are prices which are the optimal dual variants. If the price is high enough, then there will be only one person who is willing to bid on this thing. So basically, so think of these advertisers as commodities you're selling to queries, and these optimal dual variables as prices. If the price of an advertiser is high enough, then the total bid that finds that advertiser attractive is less than the budget of the advertiser. So in the extreme case, if I make the beta of an advertiser infinite, then no one is interested in that advertiser, right? So I see this algorithm never uses the advertiser. If I just like set the beta of an advertiser larger than 1, then nobody is even going to be interested in that advertiser. So what I'm saying is, there is a way to bring them up so that you have a feasible solution, but then this is not going to be optimal. The good thing about the actual optimal arrangement of dual variables is, they are high enough that you have feasibility, they are low enough that the objective value of the dual is small, so that primal matches the dual. That's all I could say. I don't know.
I think there's a corner case where like everyone could be the same and then there could be multiple primal solutions, but it's like a corner case.
But basically all of those optimal solutions are going to be feasible.
That's right. So you can't assign to everyone, but like, yeah.
Right. So I guess Varun's point is, you might have a tie here. So when there is a tie, basically any distribution over argmax is going to give you an optimal fractional solution. And this is the kind of case that there is a vertex of the polytope that is optimal, but also there are multiple optimal vertices. So any convex combination over those is also going to be optimal.
Yeah, I agree in that case. My problem is with when that xij star could be 0. If for j's that are argmax, but who says that xij star is always positive?
The direction, right?
The other direction.
Right, but this is actually going to also be the optimal solution that I don't understand. Maybe we should take it offline. All right. So one thing I want to add is that this function so far we know it should be monotone increasing. And as it turns out, actually it's going to be convex. And convexity says something about this term. So we give disadvantage to advertisers whose money spent is higher. Okay? Why is that? Because somehow if an advertiser's money spent is higher, then this advertiser is more fragile towards adversarial queries that are coming in the future. In some sense, if I use the budget of an advertiser whose money spent is low, then I'm not actually taking that much risk because there are a lot of more opportunities in the future to use the money, we should use the budget of the advertiser. If the advertiser's money spent is really large, then somehow the remaining budget of that advertiser has more value. Even though if you use it, you get the same revenue, but then you also lose a lot of opportunity in future that probably you could use this remaining budget more efficiently. This is roughly the intuition that why we want to be less aggressive about the advertiser when the money spent is lower, and we want to be more aggressive towards the future when the money spent of the advertiser is higher. So implicitly, we like G to be convex, but we are going to see a choice of G that is convex automatically comes out of our analysis. Right? So, okay, so this is kind of like what the plan that we want to do. And actually, so we know the primal solution. We know part of the dual solution, which is this beta JS star. The only part I didn't tell you is how to update the dual variable. So let's do something. So this algorithm is kind of an integral algorithm. I'm going to define a version, which is the fractional version of this thing. And it is a little bit easier to analyze. How much time do we have? So 4:30, I need 30 minutes for the display ad, maybe 40 minutes. So I'm just deciding whether I should show you two proofs, one for the fractional version, one for the integral version, or should I go ahead with the integral version directly? Let's have a break for 5 minutes. I make that decision in a minute. Let's try to, all right, so let's try to analyze this algorithm. So we already know part of the dual solution. We are going to make the rest of the dual solution. So I'm going to start with I'm actually just going to go with the actual algorithm, that one, and try to show the following here. I expect all of you to have this picture in head, the primal and dual. Because I really want to teach the display ad algorithm. It's so beautiful that if you don't see it, I'm not gonna repeat myself. So let me just show you the ugly proof, not the clean proof. The theorem. This modified version of Adwords, and I'm going to tell you what modification is needed. This modified version of Adwords is 1 minus 1 over E minus epsilon competitive. Is half competitive when max over I and J, Pij over Pj is at 1/7. So what is the modified version? So modified Adwords. So the modification is for the sake of this lecture to make things a little bit easier. So that version also works. So beta j is going to be set to 0 once I arrives.
Oh, what C?
What's that?
What was C?
I think it's E.
E.
This is E.
Oh, okay, thank you.
Yeah, so once I arrive, match I to J star such that you need to be a little bit careful about this stuff. So J star is going to be the odd max over all J sure.
J plus J less than or equal to J.
Yeah, so kind of the same thing, but you need to be you need to have a little bit of look at it. So over all J's such that for example you can fit the B. So Bij plus Yj is at most Bj. So normally you look at Bij times 1 minus beta j. I'm actually looking at Bij times 1 minus g of Yj plus Bij after I add the bit, Yj plus Bij divided by Bj. Just a slight modification. And then that's it. So this is the algorithm.
Where does beta
Is
j show up?
Yeah,
Where does beta j show up
where does beta, oh yeah, so I'm gonna write it down. So I'm gonna basically, so after this, I'm gonna update beta j. So beta j star will be equal to g of Yj star plus Bij star divided by Bj. This is how I set beta j.
That's only for analysis, right? Algorithm. Okay.
The algorithm is slightly different, right, Connor? Because I'm basically looking at the final expense to define the. So this is basically the dual variable after you.
Okay, so Chen's question was like, the algorithm doesn't depend on beta j. That's all it. That's all.
No, the algorithm doesn't depend on beta j, right? But this is beta j essentially. It's implicitly using the algorithm. But so you can always think of it as a primal dual algorithm that you are keeping track of the betas. But so that one is actually really primal dual algorithm. It uses betas. This is looking at the beta and somehow cheats a little bit, right? Because before I make this decision, my beta is equal to beta j is equal to g by j divided by j. And I don't use the actual dual variable. What I do is, I hypothetically assume that I'm matching this query I to advertiser j. So that is going to increase the spend from Yj to Yj plus Bij. And I'm like, if the advertiser gets the bid, then this is going to be a new dual. I'm going to use the new duals in order to shape the bids. So this is a slight modification. The fractional version of the problem doesn't need that modification. The fractional version you can continuously allocate to the advertiser that is maximizes Bij times 1 minus beta, and then update the beta algorithm. But the discrete version, I didn't have time to cover the fractional version. The discrete version actually kind of like that. So this is how.
Is the denominator also Bj star or?
Yeah, this is again Bj star. So this is how I set beta j, and what about alpha? So I set alpha I to be, just to make sure it's and 1 minus g Yj star plus bij star divided by bj star. So this alpha is also coming from just like looking at the dual. Why? Because if you remember dual constraint, so the dual constraint was, hey, so alpha I plus bij times beta j should be greater or equal than bij. And you want to have the minimum alpha I possible. So that means that if I give you the optimal dual, you really need to set alpha I to be the minimum number such that alpha is greater or equal than bij times 1 minus beta j for all j's. So that is basically alpha I to be equal to maximum over all j's, bij times 1 minus beta j. And this time was the maximum, right? J star. This is why I set alpha I to be like this. And so this is basically following concurrency. As long as the only thing is you use this mapping from a spent to dual the mapping G. And let's try to analyze this algorithm. So first of all, I claim this algorithm, the two questions of why dual is almost feasible. So we fix some I and j's. Now I consider two cases. Case one, suppose when I arrives, J could fit bij, meaning that yj plus bij, but at most bj. Okay. If that's the case, let's look at the dual feasibility constraint. So we have alpha I plus bij times beta j. So what is alpha I? So alpha I is picked to be bij star at that time times 1 minus g yij star plus bij star divided by bj star. And bij beta j, whatever it is. So this is definitely greater or equal than bij times 1 minus g yij plus bij divided by beta j. Directly. And what is beta j? So in this algorithm, at every time, so if you look at this, so we have beta j to be the g of spent divided by beta. This is how we construct it. So every time that you allocate, you update the beta dual offline dual to be the g function when the input argument is the money spent divided by the notified. So this is exactly equal to g of yj divided by bj. Okay, so we are almost there. Why? Because if this thing was g of yj divided by bj, then this is yj and yj. This is yj. Sorry about that. Yeah. So if this was g yj divided by bj, then this term would have been equal to bij, and we were good to go. But it's not exactly that. So let's try to do some estimation. So g is a exponential function. I reviewed it. G is just a convex function. Let's say this convex function. I'm looking at a point which is yj divided by bj, and then a slightly further, which is yj plus bij divided by bj. All right. So if you look at the difference of the function at these 2 points, this difference, then I can say g of yj plus bij divided by bj minus g of yj divided by bj, this difference is at most is that most g of, correct?
G prime at yi over bj times
And lower bound. Is the lower bound? Upper bound is.
so you need a lower bound on this. Upper bound on this, which would translate
It really
to.
doesn't matter. So I actually upper bound. So this is upper bounded by what? So it's upper bounded by let's look at the tangent line at the g function up here. If you look at the slope of this line multiplied by this difference, then this is going to be basically the new progress. This thing. Right. So this quantity is at most this quantity, which means that is at most g prime at the point yj plus bij divided by bj times bij divided by bj. And this is convex, so this is at most g prime of 1 times x. So this is basically what I'm trying to use. So having this inequality, then this is going to be basically greater or equal than bij times 1 minus g yj divided by beta g divided by bj minus g prime of 1 epsilon plus g yj divided by bj, and these two terms cancel, and this is going to be bij times 1 minus g prime of 1 epsilon. So this is almost feasible if epsilon is small. So let's try to look at the second case when you cannot fit into the budget. So case 2. When I arrive, yj plus bij is essentially more than the budget of the advertiser. In that case, I can say alpha I plus bij beta j. So j has spent a lot of money. It's almost at the end. Therefore, beta j should be large enough that can cover the edge. So this is greater or equal than bij times beta j, and this is equal to bij times g of yj divided by bj. And you know, we know yj is greater than bj minus bij. So this is because of monotonicity of g, this is greater or equal than bij times g of bj minus bij divided by bj. Right? Which is equal to bij g of 1 minus bij times bj. So now let's look at the situation. So again, the same convexity argument. So we have g function, there is a point 1, there is a point which is 1 minus bij divided by bj. I can again say that g of 1 minus, basically, I want to say G1 minus G of 1 minus Bij divided by Bj is at most G prime at 1 times Bij divided by Bj, which is at most G prime at 1 times epsilon. And therefore, if this is true, I can say this is greater or equal than Bij, replacing this lower bound we get on G of 1 minus Bij over Bj from this inequality. It's going to be greater or equal than Bij times G of 1 minus G prime of 1 at epsilon. And let me remind you of something. So we had this G function. G was a mapping from 0, 1 to 0, 1. We need G of 0 to be 0, and we will see that for second by. G of x was monotone and convex. I'm going to add, so we want this to be almost feasible. That means we need G of 1 to be 1. And let's write it down here. So I also need G of 1 to be 1. So these are the required conditions that they have, that they need for G. We're going to get back to this at the end. All right, so if that is true, then this is going to be equal to Bij times 1 minus G prime 1 epsilon. So we have almost feasible.
So if we make G of 1 to be 1, then we no more need to search in the argmax over feasible solutions, right? There. Now we can search overall and it'll automatically be 0 for all of them for which you
have to, well, so you don't want to really allocate if the
yeah, it'll not get allocated because now G of 1 is 1.
Yeah, I think you're right. I think you're right. So this gets so you need to say that, hey, if all of these numbers are negative, don't allocate. Yeah. So basically don't allocate to negative ones. So I need to look at basically a dummy advertiser that has bit 0 for everything. And if I add that dummy advertiser, I can just go with the argmax. If all the shaded bits are negative, I'm just sending my query to that dummy advertiser. Okay, good. So let's try to do the same thing that we did for greedy, which is comparing the
Case 2 basically says no one can buy this, right? No one could have bought this for
Right.
one.
Right. If no one can buy this, that means that already those advertisers, they have spent enough money that they can cover the dual constraint. If that makes sense. Right. So this is part to not order. Right. So the next lemma, why is approximately optimal in terms of objective. This is actually kind of fun. So you will see in a second why did I that check. So imagine that this beta arrives, you assign I to J star. First of all, if there is no one you can assign, but how much dual and primal changes? So if no one can accept the bit, then delta primal is 0. Delta dual is also 0. So in that case, you're good to go. So I'm not going to go over that tree. So the actual case is once I arrive, you match I to J star. Okay. In that case, delta primal would be equal to Bij star. The cute part is delta dual. So what is going to be the delta dual? The delta dual. So only two dual variables are going to be impacted by this decision. Alpha I and beta J star. So this is equal to delta of alpha I plus delta beta J star. So alpha I was 0. Now it is. What's that?
BJ times delta BJ.
Yes, thank you. And all right, yeah, so this comes out of the first order conjugate, but yeah. You just made me nervous that my proof doesn't work, but it works. Yes. Any question? I heard something. So this is the change the dual objective, so delta alpha I times delta beta j times bj. And Chen mentioned this bj because if you remember the objective of the dual, it was summation of alpha i's plus summation over j bj beta j. So okay, so alpha used to be 0. Now it is 1 minus g of so alpha I is 1 minus g of
Bij. Bij.
okay.
Bij.
Yes. So it is good. Thank you. This Bij times 1 minus g of y Bij star times 1 minus g of yj star plus Bij star divided by j star. What about this guy? So it is basically Bj times, let's do that. So it's going to be g of yj star plus Bij star divided by Bj star minus, yeah, this is a star too. These are all stars. Minus g of yj star divided by Bj star. Basically, the money spent on J star was yj star divided by Bj star. Sorry, the money spent was yj star, the normal money spent was this quantity. Now, J star is spending Bij star more, and we know that the dual has this invariant, it is always equal to g of normalized money spent. So therefore, this is going to be a change in the beta J star. Okay. So far, so good. Now, freedom is here. Yeah. So now think of this term again. So we have the convex function. This is yj star plus Bij star divided by Bj star. We have this number here, right? So we can always say that this is yj divided by Bj.
Bounded by G prime.
I'm going to find the upper bound on this thing. So this is now, this time is going to be upper bounded by
G prime 1.
right. So G prime at this point. Right. So G prime at this point times the difference. It's going to be. Okay, so this is Bij star. Let me just use this notation. And then we have Bj star times what? So this is no more than this one, Bj star times. So this is G prime at this point times the difference. So G prime at the point yj star plus Bij star divided by Bj star. This is, and you see this term is exactly this term. This is the only reason I did the modified analysis. Otherwise, I couldn't get a fully multiplicative term. So I wanted to get a fully multiplicative, this is why I made that change. So it's going to be Bij star multiplied by this thing
Bij star
times Bij star divided by Bj star.
Bij star go away.
So this cancels. And now you will have a beautiful differential equation. So,
Oh. And you get the G of blah, 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 Bij equals G prime of blah, 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 Bij.
exactly. So delta dual would be at most Bij star times 1 minus capital G of Yj star plus Bij star divided by Bj star plus G prime at the same point. Yj star plus Bij star divided by Bj star. It's the same math. All right. So we know it is almost feasible. Then imagine that I can somehow make this term to be a constant gamma. If I can do that, then I can say delta dual is at most Bij star times gamma, basically gamma times delta prime on for this allocation. The change in the dual will be at most gamma times the change in the primal, or change in the primal is at least 1 over gamma change in the dual. Now, if G of 0 is 0, meaning that my dual assignments at the beginning are all 0, then you can say by just adding these partial changes throughout the process until the end, I will have my primal at the end to be no smaller than 1 over gamma times my dual, which is actually a physical dual, an almost physical dual. So let's call that, yeah, so this is dual. So now to make things feasible, so I'm gonna look at the dual prime, which is equal to the previous dual divided by 1 minus G prime 1 times epsilon. Then I can say my primal is greater or equal than 1 over gamma times 1 minus G prime of 1 epsilon times the dual prime. So this dual was almost feasible, uptown epsilon, this is exactly feasible. It is a feasible for a dual solution, so this is greater or equal than 1 over gamma times 1 minus G prime 1 times epsilon. The opt of dual is a minimization problem, it's a physical solution, and a strong duality, this is equal to the optimum prime. So it's 1 over gamma times 1 minus G prime 1 times epsilon times the actual opt. So this algorithm is going to be 1 over gamma complexity. And now we want gamma to be as small as possible. G0 should be 0. We had G1 to be 1. G should be convex, G should be monotone. We have used all these properties. And we want this thing to be constant. So what will be a function form that is constant here? Yeah, so basically, as long as you have any exponential function with exponent equal to 1, then this is going to be a constant. Let's try to find the function. So let's say g of x is equal to a plus b e to the power x. Then first of all, I know 1 minus g of alpha plus g prime of alpha is equal to 1 minus a minus b e to the power x plus b e to the power x is cancelled, is equal to 1 minus a. So perfect. Second, I want to have g of 0 to be 0. So that means, why do we need g of 0 to be 0? So that, when you keep track of these partial changes throughout the process, the initial point of dual to be 0,
So that you can say primal is at least 1 over gamma times 2. What does that mean? So that means that A plus B times E should be
B just plus
E
B.
should be equal to 0, so A should be minus B. All right. And then the second condition, G of 1 should be equal to 1. Where did we need that? When we are thinking about the almost dual feasibility of dual, so we need G of 1 to be equal to 1 in one of the cases. That means that A plus E times B should be equal to 1. If you solve these three, G of X is going to be equal to E to the power X minus 1 divided by E. So it checks all these conditions. And then from this, gamma is going to be equal to 1 minus A, which is 1 plus 1 over E minus 1. So it's going to be equal to E over E minus 1. And this is the end of proof. So the algorithm is going to be 1 over gamma completed, which is 1 minus 1. And this is a beautiful result. And I mean, if you are wondering how it is related to the fractional version, whether the fractional version is easier or not, come to my office this week and I would be happy to explain that to you. But this was a little bit ugly simply because of the fact that I tried to analyze the actual integral algorithm. The fractional one, you don't need to be worried about bits to be bits to be very small compared to the budget. Basically, if you look at the fractional version of the problem, then you can allocate bits fractionally without any assumption. The algorithm that is continuously matching the arriving I to the j with maximum bij times 1 minus beta j is going to be 1 minus 1 over incomplete. But we are not analyzing it. But now we are switching to display ads, and there you will see actually a fractional algorithm.
So okay, question.
Yes.
So I was thinking, so we are doing some like gradient descent or mirror descent on beta G. Is there any relation to this?
There is actually a nice relationship to that. So basically, come to my office, I will explain. So I have a paper which shows, maybe actually for the special cases, actually already know, but for the general case. So what is the result? It says that this operation that you're making at each step, when you plug that exponential function, is actually solving a regularized version of the greedy problem. So the greedy problem for, so let's say a query IRS. What does greedy do? So greedy picks a xij that maximizes summation xij bij subject to subject to basically summation xij over all the advertising atoms. That's like max function. As it turns out, if you regularize this with a certain convex regularizer, it is actually summation over all the advertisers, 1 minus e to the power of yj divided by bj minus 1. If you regularize the objective with this term, and now you try to, so you start with some initial water levels, initial spend by 1 to yn, and then you find the allocations such that, sorry, this is not at most 1, so this is at most basically this plus the current consumption is at most bj. So this is the constant you have to. So what I'm saying. So query advertisers.
In this case, you need the VHA.
I think you are Lagrange relaxing.
Actually, I'm not Lagrange. So let's say one IRS. So then I'm summing over j. First of all, I want the summation over xij over all j to be at most 1. And second, what I want is, for every j, xij that I'm allocating plus their current consumption to be at most bj.
Dij times xh.
What's that?
Dij times xh.
Right. So this is basically a sub problem that you solve when I query IRS. So if this term does not exist, then this is what the grid does.
right? Basically, among those that you can fit, you give to the one that has maximum DH. If you add this regularizer, then now we have a convex program to solve, a concave program to solve. As it turns out, if you run coordinate ascent, a version of gradient ascent on that concave program, then the primal solution would be basically following the fractional version of the Adwords algorithm. And if you use the essential duality to find these optimal dual variables in the convex program, they're exactly the optimal duals that we use in this online algorithm.
So the second term is the balance or the fairness.
Yes, in some sense, but it's a very, very structured term. Uses the exponential function and everything. There's a deep connection between basically regularized convex programs and what's happening here under the hood. And I have a paper that says, if you want to optimize this competitive ratio when rather than arbitrary number of queries, you have, let's say, 5 queries. How you change this regularizer over time, that gives you the optimal competitive ratio for a certain number of variables. That's topic for another day. So let me do the display add problem, which is very nice. So what is this application? There are different, again, advertisers. And then there are different websites that the publisher, there are different publisher websites, like for example, Wall Street Journal, New York Times, etc., that they have ad display opportunities. Users go there, for example, I go to this website and I'm just like reading an article. As I'm reading the article, potentially there is a chance that an ad will be shown to me as I'm reading the article. So this is basically, it's going to create an impression to me that, hey, I have to go and buy that product. So the fact that I'm using this web page is basically creating an inventory for impressions. And then there are advertisers that are willing to actually pay for these impressions. And now Google sitting in the middle as an intermediary is called Ad Exchange, AdX platform. They match the impression inventories that are created as people use websites and go to Wall Street Journal, New York Times, to advertisers who are willing to pay for these impressions. So basically the mental image that you should have in mind is that we have web pages arriving. And I say web pages arrive, what I mean is users go to different web page. So once a user goes to a web page, there is an opportunity for creating impressions. So that's an inventory of impressions. Now, Google is sitting here, the AdX platform, has signed some contract with the advertisers. There are advertisers that are interested to show their ads. They need a certain amount of impression. So this advertiser needs N1, this needs N2, this guy needs NM, and probably the bad notation, but I'm going to stick to the notation of the original paper. So N of A is the number of impressions that advertiser thinks. So when a web page arrives, each advertiser is willing to pay different amounts for that impression. Just for the sake of simplicity, assume that each web page only has one impression. So a web page arrives with the opportunity of just showing an impression, one impression. Each advertiser, advertiser A for impression I is willing to pay WIA. So WIA is basically the bid of advertiser A on impression I. page I that has just the single impression. Yes.
What do you mean by impressions? Sorry, I don't.
So I go to Wall Street Journal, I'm browsing, reading articles. At the same time, Wall Street Journal can have ads on the left-hand side. But these ads, so it's not WSJ who is picking which advertisers should actually use that as well. They go to Google. Google has a service called Display Ad or Ad Exchange, which connects the advertisers to publishers. And then they're like, okay, so give me an advertiser who is willing to pay for this impression. Then Google receives these bids, decide which advertiser should be matched that page. The ad of the advertiser will be shown on that page. And it's called assigning an impression to the advertiser because it's not about search. So I'm not searching, it's not the search engine. It's just like I'm browsing at the same time. The fact that I'm just like seeing the ad is something that the advertiser is willing to pay for. So
I don't get the difference between search ads. It's still Google is searching.
I'm not searching. So there is no search engine here. So in the matching of the queries, so this is really an application, by the way. It's not something I'm making up. So in the search ads, so there are queries and there are advertisers. So the users go search something, a keyword. And that certain keyword will be kind of matched to an advertiser who is willing to show his ad for that keyword and is going to pay for it. So here, I'm not searching anything. I'm just like browsing, going to different publishers' websites. As I go to a publisher website as a user, opportunity for creating an impression is built. And then the goal of the AdX is matching that opportunity to one of the advertisers who is willing to show his ad at that time on that website. But mathematically speaking, the problem seems to be very similar because there are these bids. The only difference is that the type of contract that these advertisers have with AdX is not that they have a daily budget. This time they need some certain number of impressions. Yes.
So instead of a packing, we have a covering. So instead of a packing problem, we now have a covering problem.
Good. So
It's a mixed packing
it
problem.
is still a packing problem in the sense that
You need to pack one impression.
so you need to pack one impression. So you have a definitely packing. So basically, you need to give this impression to one of the advertisers. So you have a packing constraint on this side.
You have a
On
covering.
this side, I don't really have a packing constraint. I can give as many impressions as I want to this advertiser.
The cover.
Wait a second. But this advertiser is only willing to pay for the top NA impressions that you assign to this advertiser. So the advertiser says, okay, I need 100 impressions. So as the publisher, you might actually assign more number of impressions to this advertiser, but then the revenue that you generate is only for top NA impressions that is assigned to the advertiser. That's the main difference between this problem and the previous problem. So let me actually write it down in boards. You can assign.
So that's how many they need. It's the top that they are paying for.
Kind of like that. And the reason is, so it's kind of like they need this number. So you can assign more, but then they're going to dispose that in some sense. This is why this assumption sometimes is referred to as free disposal in the literature. So you can assign as many impressions to advertisers but, which is really important, they only pay for top NA impressions.
Why should we assign more than that?
If Optimum Offline never assigned more than that, but Optimum Online might actually go and assign more than that because it doesn't really know the future.
Doesn't online problem knows all of NI?
It knows the NIs, yes.
So
Because in the beginning, you might have bought, people might have assigned something very cheap, but now they are willing to pay $10,000 for an
Exactly.
impression. So you want to assign that, although they already control.
Exactly. So this is a very important example. What was your name again?
Constantinos.
Konstantinos mentioned. So basically, imagine that I have these two advertisers, right? And then this guy arrives. Actually, with one advertiser, you can. Oh, with so this guy arrived, and then I'm matching. So the money here is 1, here is like double, right? So let's say both of them are 1. Both of them are 1. So I assign the 1 impression to this, and each of these guys only need 1 impression. So N1 is 1, N2 is 1. So now their capacity is full. Now a new resource, a new inventory of impression comes with 1 more impression. But this time, actually, this guy is willing to pay W for that, and W is 1,000. And now this is actually the time that you wanna again assign this impression to this guy. He's gonna pay for the top impression. He's gonna dispose this 1 impression that you assigned earlier. And if the statement of the problem wasn't of that sort, basically it was like, you cannot assign more than the number of impressions as an online algorithm to the problem, to the advertiser, then here, the online algorithm would have been unbounded with that. Because if you make an irrevocable decision to either of these guys, then I can just like shoot an edge which weights infinity to that person. And because you cannot assign this anymore to that, you already exhausted that advertiser's quote unquote budget, then the online algorithm is going to be unbounded. About that, while the offline algorithm could make the right decision and match it correctly. Is it clear?
Yeah, so in this case, compared to the previous problem, there are only 2 differences. First, the constraint on the advertiser's side is the number of their impression, not their budget size. And second, we can
I would say
more
just
than
like one major difference mathematically speaking. The rate at which you generate revenue is different than the rate at which you consume budgets. And because of that, I'm adding this extra flexibility in some sense, aka free disposal to be able to design an online algorithm. But this is actually coming from the practice as well. Like this assumption is well motivated because these advertisers, they have this kind of contract with Google. And hey, I need this number of impressions. You should feel free to give me more impressions, but I'm just gonna pay the top impressions within the number of impressions that I need. I'm just gonna get rid of, as advert, I'm just gonna get rid of freely disposed the low value or low bid impressions, and I'm paying for the top one. It is your loss. I'm not paying for it. But still, with this restriction, you can design an optimal 1-1 algorithm that's called linear.
When we talk any, it's chronology wise, not bit wise.
Bitwise. Yeah. And because of that, let me actually start introducing a concept, which is a key concept in this program. So previously, I could just capture the state of an advertiser by just one number, which was the money spent of that advertiser. So we had YJ, which was the money spent, and it could capture the state of an advertiser. But now if I look at advertisers, so the advertiser has paid for different impressions at this point. So there's a collection of impressions that has been assigned to the advertiser. The advertiser has different bids on the impressions. And if you now assign a new impression to the advertiser at a certain revenue, at a certain value, then you only get the revenue of that thing if there is something worse than that that has been given to the advertiser advertiser can get rid of that and then acquire the new one that he wants. So imagine that the advertiser's capacity is filled with a collection of different impressions at different levels of revenue. So if I give an extra impression to the advertiser, then the advertiser can only enjoy that if she can get rid of something, fits this in. And for this to happen, the advertiser needs to have some amount of allocation at a lower level of revenues to get rid of that and get this extra weight. Okay, so this seems to be a little bit complicated, but I'm going to define a state variable now, which is playing the role of the money spent, that captures this kind of situation in the problem. So for advertiser A, I'm going to define YA at level W, which is now, this one was just a number, now it is a function. So YA of W to be equal to summation of all the allocations XIA to this advertiser from different impressions. But I'm only looking at those impressions that the revenue was more than this level W. So I'm looking at all the impressions I such that WIA was greater or equal than W. So this defines the function. So let's call that the level function. So these level functions, by definition, they have a step function structure. So if you think about a level function as a function of W, so imagine that this advertiser has a portfolio of weights, W1, the smallest weight, W2, W3, all the way to some number WK, where W1 is smaller than W2, is smaller than WK. Each one corresponds to one of the impressions that has used this advertiser. Then the level function is kind of like a CDF, inverse CDF. And let me actually look at the normalized version. So it really becomes like an inverse CDF. Then this level function is going to be 1 for all the ways before W1 because everything is greater than 1. And suppose I have filled the capacity of the advertiser. So advertiser has some amount of W1, some amount of W2, some amount of WK, and their summation is equal to 1. Basically, or equal to NA, meaning that the entire, I have given all the impressions that the advertiser needed to the advertiser at these different weights. And now I look at the function Y. So how much allocation do I have for weights greater than 0? So it is equal to 1. If you look at the normalized quantity.
Y, X, it could be greater than 1, right? Xi could be equal to 1 for more than any impressions.
No, so imagine that I give more impressions to the advertiser, but the moment that I give more impressions, I gets rid of the smallest ones. So
Xi is.
So if you're interested in 100 impressions, I give you 120.
Xi is not capturing what was given, what stays, essentially. What the impression for which the bit stays.
Correct. So it's basically the impression that the advertiser at this point is responsible to pay for.
Okay.
So XIA is how much of impression I, advertiser A, is responsible to pay for at level of WIA, essentially. So this is the main goal. Then it's going to start at 1, they become some smaller number, they become some smaller number. And then after WK, so no assignment more than WK has happened to the advertiser, this is going to become 0. All right.
So is the impression of I is same for all the advertiser or?
No, so the impression can have different weights for the advertisers.
or different revenues.
Okay, so I probably don't understand the problem that well. So
Yeah.
how to understand the impression? So what is impression?
So impression is basically like there's this web page, the user comes to the web page, so it's an ad opportunity. And different advertisers are willing to pay differently for this ad opportunity. And these WIAs are how much they're willing to pay for this ad opportunity. That's what your question was about the application, right?
Yeah. So so how much they willing to pay for this advertised spot, right?
Right.
And so what's the impression?
So the impression is basically, so I think this is the kind of like terminology that people use in this industry because you create an impression on the user who is visiting that website. And the impression eventually is gonna hopefully be converged to a click or something like that. At this point, maybe it's not a click, it's just the fact that someone is seeing your ad is creating the impression on that person, and later on, the person is gonna buy the product. So this is why this kind of ad opportunity in this industry is called an impression.
Okay, so can I understand that? Can I think that so different I have different impression for different like advertiser because it's kind of like different spot on the web page.
Oh no. So don't think of it as so in this very simple version of the problem, each of these things is just like a website that someone has, started browsing into. And that has created one ad opportunity. And now different advertisers are willing to pay differently for this ad opportunity. And each one has already a contract with Google that says we are interested to pay for at most a number of ad opportunities. And we are only paying for the top ones, not the ones that our bid for them is small. Top in terms of like they sort the different opportunities based on their revenue, their bid, and pay for the top and eight. If it makes sense. Yes.
What's XIA here?
Good. So XIA is how much at this state of the process, advertiser A is responsible to pay for impression I.
What do you mean by this is state of the process?
So eventually you're thinking about an online algorithm is as pages arrive is assigning these impressions to advertisers. So many of these questions are going to be resolved once I write the linear program for the problem, and then you will get to see this. You will understand this more. Just give me a few minutes and then you will see it. So this was just one primitive I wanted to define early. Now, if I want to think about an optimum offline algorithm that knows the instance using knows the instance and solves the optimum solution using a linear program, then this is the simple linear program that you have to solve. Pretty similar to the one that we saw with some slight modification. So we are trying to maximize summation over all impressions I and all advertisers. I'm just saying impressions because assuming each web page has just like one impression. Sum over all I and A, XIA essentially is going to be 1 if impression I eventually is assigned to advertiser A. It's going to be 0 if impression I is not eventually assigned to advertiser A. And I say eventually because there is this free disposal happening throughout the process. So you should really think of XIA is equal to 1 if eventually when you're calculating revenue, advertiser A is responsible to pay for this impression. And we can also fractionally assign impressions to advertisers potentially. So XIAWIA subject to, first of all, for every impression I, you should just assign it to one of the advertisers. And second, if you look at each advertiser, basically, you should not give more than NA to that advertiser in the offline solution. So summation over all impression I, XIA should be at most NA. It's pretty similar to the previous one, but the main conceptual difference is that the rate at which you generate money
by assigning an impression to advertiser is different from the rate at which the capacity of the advertiser is consumed. And that makes the problem difficult. Right. So this is the primal problem. This is now the dual. So the dual is going to be, you're trying to minimize. So this is alpha I, this is beta A. We're trying to minimize summation alpha I over I plus summation over all A and A beta A such that, again, you cover every edge. So for every pair of advertiser and impression, so you want alpha I plus beta A to be greater or equal than WI. Okay. And alpha I and beta A should be greater or less. This is a dual problem. Okay, so the first thing, the magician's algorithm. So if a magician gives you magician online algorithm, magician based online algorithm. So if a magician gives you beta A stars, I'm not going to repeat the same argument using complementary slackness, but actually you can say, here is the optimum algorithm once I arrives. Match I to A star such that A star is the argmax of this time WIA minus beta A star over all advertisers. It's pretty much the same argument as before. And now from this structure, we can guess a primal dual algorithm. So this time, I'm going to make my life a little bit easier, so I'm really thinking about the problem in which these NAs are large, and I'm assigning impressions integrally. I'm thinking about the fractional version of the problem, in which once an impression arrives, you can fractionally assign it to different advertisers. So basically, you decide on these XIAs, they can be any number between 0 and 1, but you have to make these decisions in an online irrevocable fashion. Similar to online fraction matching that Warren covered in the previous class. It's kind of like the same type of online algorithms. Still, it is online, you don't need to make integral decisions. And if you want to follow the previous recipe that we saw, I hope I can finish it up in time. And this is going to be my optimal display allocation algorithm. Optimal display allocation. So start from beta J0. Now, so beta A0. Now, once I arrive, continuously allocate I to A star, which is the argmax of WIA minus beta A over all the A's such that WIA is greater or equal than beta A, and continuously update beta. The way to think about it is, I have this impression I, let's say I'm going to allocate an infinitesimal dx amount of this impression. So I'm going to pick a star at this point, which is equal to argmax of WIA minus beta A. So there is one advertiser that maximizes this quantity. Think of advertiser A star, so it is this advertiser. So for this advertiser to get WIA, he should get rid of something. I'm gonna pick a name for that. So you assign this WIA to the advertiser times dx, basically dx amount of this quantity. So you assign dx amount, and this is the revenue that you generate. And then the advertiser should get rid of dx amount of something. So this is the free disposal in order to accept this allocation. And there is some certain number that she's going to get rid of. Let's call that WIAO. This quantity changes during this fractional process because as you assign, the advertiser is going to get rid of the smallest weight, but this smallest weight might change as you go through the process. But it's something. Let's call it WIAO. That is going to get rid of exactly the same amount so that can accept this impression. And now that you assign this, update beta A. So we're going to update beta A, and this is the crucial part of the algorithm that I haven't yet told you how to do it, and continue, right? So the algorithm is well defined, right? So I'm keeping track of these dual variables, continuously assigning to the advertiser that maximizes weight minus the dual, update the dual, and continue until I'm at the end of the day. So this is the part that the level function comes into the picture. So throughout, so remember, so what was the connection between the money spent and the dual variable in the previous algorithm? So it was a monotone function of the normalized money spent. Here, you will do the same thing, but you will replace the money spent somehow with this level function that captures more information about this portfolio of impressions that has already assigned to the advertiser. I'm just writing down the invariant. This is the genius part of this paper. So you want to have a beta A throughout this process. So that beta A is equal to the integral from 0 to infinity of g of y w dw. And just to compare it with previously, we had beta j, it was g of essentially yj. Because here, I have already normalized y. If you think about y as the normalized water level, so this is really what we had before. It's kind of like you still use this g function applied on the money spent, but rather than money spent, you have this higher dimensional object, which is actually function, the level function. And then you essentially, at each certain level, weight level, you apply to the money spent at that level, and then you sum over all these different levels. So this is the best intuition I have for why do you want to have such an invariant. Kind of a natural extension or generalization to the previous language. So you want to have this invariant, and in order for this invariant to hold, so suppose I allocate this amount. So if you look at the level function after this allocation happens, so you have a level function like this. This is the smallest weight, WIA old, and this is the new weight, WIA, that you're allocating. So you are getting rid of basically the X amount of this thing, and you're increasing WIA dx amount. So if you think about this, the only thing that will be different is going to be the level function between these two quantities. So basically, the level function between these quantities is going to be increased by dx at all these levels. Basically, the new level function is going to be this one. And it doesn't change for weights that are smaller than the WI old and larger than WIA, simply because of the definition here. I don't know if this is clear, but first of all, if I'm allocating something at this weight, for any weight that is larger than that, the amount of allocation doesn't change. For anything in between, the allocation is going to be increased by the X amount. And then for anything below that, the allocation again doesn't change. It's just a coming from this definition. And now thinking about this formula, if this is the invariant you want to preserve, that means you have to update your beta A in this process by saying that beta A is the previous beta A plus the integral from WIA old to WIA little g, the first derivative of this function, by W dW, this quantity times dx. If you update or multiply by 1 over NA. Actually. So let's try to prove this. I claim that if you update beta like that, then you will have this invariance. This is not that hard to see. And then we'll find the, I'm writing a theorem and hopefully a assignment of the alphas. Maybe I leave the final proof as an exercise. It's not that hard, given everything that we have. The lemma with the update equation, the star, this one. In the update equation star, we always have beta A to be equal to the integral from 0 to infinity g of y w dw. So kind of the proof is by induction. Imagine that this invariant holds at some point, up to some point in the algorithm. I'm going to show you that it's going to continue to hold. Suppose I do this allocation. Suppose BA hold the current value of the dual is equal to the integral from 0 to infinity g of y old w dw. We show BA new after you do this fractional allocation is as we want. The thing is, just look at the difference, integral from 0 to infinity, g of y mu w dw. So this times dx. This is the change in the dual, right? So, so look at this difference basically. So only between the two weights that are important in this step of the process, y w will be different. Everywhere else, y w remains the same. So then this is going to be equal to essentially integral from wi old to wia, the new one, g of yw old plus delta x that I have allocated divided by na minus g of y old w plus plus 0, same thing, dw. And then this is infinitesimal amount, so this quantity is now going to be equal to g of ya old w times dx divided by na. And we know that this was basically our beta A old before we do that continuous update. This was exactly the term that we added. Therefore, the invariant is not remain. This here, so I'm just asking that suppose beta had this form, I increase dx amount by adding WIA, getting rid of WIA old. And then I'm keeping track of how this thing changes as I make this this move, basically increasing only YW between W old and W new by dx amount. And this is exactly the term that I added, so that means that the new beta will be equal to this quantity. Okay, good. So far so good. So now here is the main theorem. The theorem. I just need like 5 minutes. This algorithm is 1 minus 1 over E component. So proof. So we already know how to define beta A. Beta A throughout the online process is going to be always equal to the integral from 0 to infinity g of ya w dw for every A. I just need to show you how to update alphas. So once allocate the X amount impression I to advertiser A, then set alpha I to be the previous alpha I plus dx times WIA minus the beta A at that. And that's it. So this is how you construct the dual assignment. As you're producing your allocation continuously, construct the dual using this updated version. So when you match I to A, just increase alpha I by this amount. If you look at the lecture, it is exactly how we updated alpha I for the Adwords problem in some sense. So it's kind of following the same recipe. Now, let's answer the 2 questions that we always ask. Why dual is feasible? Well, think of fixed sum pair IA. 2 cases can happen. Case 1, impression I could be allocated fully in this continuous form.
Meaning W only is 0.
Meaning that I never reached to the point that there is no advertiser
Oh,
whose
sorry,
beta
yeah,
is smaller than W until the point that I have allocated all one unit of my impression. It's continuous. So basically, the 1 unit of impression arrives, the continuously allocated, you can allocate it and never for each advert so never you get to the point that for all of the advertisers, their current dual variable is as high as the marginal revenue could get from. If that is the case, then so throughout this process, we know that d alpha I divided by dx is similar to the proof that Warren actually showed in the previous course. We know d alpha I divided by dx has been equal to WIA minus, has been at least equal to WIA minus beta A at that time, right? So basically, at any time in the process, you're always matching to the guy that has the maximum, the WIA minus beta A. That means that at every time in the process, the rate at which you're increasing alpha I is at least WIA minus the beta of this advertiser at that time. And then you know if this beta is increasing, that means this is going to be definitely greater or equal than WIA minus the final beta of the advertiser. And because we have allocated 1 unit fully, that basically means that alpha I is going to be at least basically the integral from 0 to 1 dx of the constant rate WIA minus beta A, which is equal to WIA minus A. And that is the frequency. So that means that alpha I plus beta A is greater than alpha I. And then the case number 2 is, at some point in this process, you had to terminate, you couldn't allocate more from I. So when does this process stop? The process only stops if all the advertisers, their corresponding B is greater than A. So if process stops, it just says that at the time that it stops, beta of A itself was greater than WIA because you couldn't allocate to A. And this means that already this advertiser can cover there. So WIA plus beta A is already, sorry, the beta alpha I plus beta A is greater or equal than beta A, which is already greater than WIA, and therefore you're good to go. This is kind of like feasible by definition. Let me write down the other lemma. And then the class is finished. So lemma basically we are trying to answer the question that why dual is approximately feasible. So lemma is that during this continuous process, anytime that you allocate, delta primal, the change in the primal, will be at least 1 minus 1 over E times the change in the dual if g of x is e to the power x minus 1 divided by e to the minus 1. And let's see the proof. It's kind of like one line. So what is delta primal? So again, just like to recap, I arrives, you match I to A star. You basically match dx amount of I to A star at revenue WIA, and A star gets rid of dx amount at revenue WIA old. Okay, so delta prime out would be equal to WIA, so you gain this amount times dx, but you lose this revenue. So WIA minus WIA old times dx. What will be delta dual? If you remember the dual assignment, so data, so it's going to be basically alpha I plus NA times delta alpha I plus NN times delta beta A. And by the way, all of these things are the star. Let's say I am matching I to A, just not carry this as star notation. Right, so this is easy. So what is delta alpha I? I had a formula for it, like dx times wi minus beta A. And what was delta beta? If you remember the opposite equation of beta that I wrote down. So it's basically NA times 1 over NA integral from WIA old to WIA little g of YW dw. That's all these cancels. Multiplied by dx. So this is equal to dx times. So I'm writing this down as WIA minus WIA old plus WIA old minus integral from 0 to infinity g of y w dw plus integral from WIA old to WIA little g of YW. So this is basically this term. Beta is always equal to this quantity. I just added WIA old and subtracted WIA old. And here's the funny part. So this is equal to dx times WIA minus WIA old plus. So WIA old can be written down as the integral from 0 to WIA old of G Y W dw if G1 is equal to 1. And let's see why this is the case. So if you remember the shape of the YW or the definition of W old, the YW is always equal to 1 all the way to the smallest weight. This is the one that you get rid of when you do the free disposal. So that means that, so y is 1, so then this is going to be constant in this interval equal to g of 1. So then this is equal to g of 1 times where this step, so there's some of the, where this step happens, there's going to be g of 1 times WIA old. But if g of 1 is equal to 1, this is just WIA old. Yeah, this is kind of a proof from the book, but let me finish it. It's a little bit algebra here. And then the rest. All right. And this is equal to what? Now you should start seeing a familiar differential equation here. Right, so this integral minus this integral is just the integral from WIA old to infinity of G by W. And now this is equal to, if G of 0 is 0, we know this function by AW is always 0 after the largest nearest weight is WIA. So here it is 0. So if G of 0 is 0, then you can write down this term as the integral from WIA old to WIA A itself, G by W0. So this becomes dx times WIA minus WIA old. I'm just writing down the previous terms. Now the difference between these two integrals by default is the integral of the same function from WIA old to infinity. But then after WIA, the YW is 0. So if G of 0 is 0, that means G of YW is going to be also 0. So it becomes the integral from WIA to WIA old of G of YW dW. And then I'm just like carrying the other term, the same lower bound and upper bound integral outside. This is old, this is new. And here I have the little g function.
And why is it 0 after YA? It doesn't have to be the highest, right? There could be more items which are profitable.
Yeah, I think so. So this is enough if you want to have a lower bound. If you want to have an upper bound. You're right, absolutely. So, all right. Now, do you see the differential equation? This is the one that we always have. Dx. Let's write this down as the integral from WIA old to WIA of 1. So then the whole thing is going to be integral from WIA old to WIA of this thing. 1 minus G of YW plus G prime of YW. PW, that's it. And we know this magical function, when you plug it here, this is just going to be a constant. And the constant is E over E minus 1. So this becomes dx times E over E minus 1 times WIA minus WIA old. And this is the change in the primal. So this is E over E minus 1 times delta. That's it. So it's kind of like a magical generalization of the previous primal-dual algorithm and analysis. But the key idea was using this level function and defining beta to be a similar invariant, replacing the money as a scalar number to a higher dimensional object, which is the level function. All right, yeah, sorry for going a little bit over time. Hope you find this lecture interesting. So the next lecture is going to be about a problem that has application in online retail called online assortment optimization. We are going to talk about the adversarial version and then the Bayesian version. And we talk about the connection to a fundamental problem called contention resolution. It's online version. Varun touched it a little bit in the previous quarter when we saw how to design the profit inequality algorithm from the linear programming. But we are going to dig deeper into that in the next. Okay. Don't forget about the strike.